Bueno, vamos a decir que se puede grabar, listo. Muy buenas tardes a todos, muchas gracias por su tiempo, por estar aquí presentes, por su interés en esta reunión técnica que nos convoca hoy de parte del Grupo Colombiano de IABSE. Les doy la bienvenida y de la misma manera quiero aprovechar para hacer un agradecimiento al profesor Jorge y a Carlos Arteta, Jorge, no sé cómo se pronuncia Jorge, Archibald, no sé, pero muchísimas gracias, ¿cierto?, a la Universidad del Norte por todo el apoyo que nos han dado para poder llevar a cabo estas iniciativas que ya les contaré un poco del Grupo Colombiano de IABSE. Muchísimas gracias a todo el equipo administrativo de la Universidad del Norte. A Melissa, muchas gracias porque has estado ayudándonos bastante en toda esta programación, en este primer evento y el evento que tendremos dentro de 15 días. Y a ustedes, todos los estudiantes de la Universidad del Norte que fueron convocados, que están asistiendo y que están conectados, muchísimas gracias. Desde luego, agradecer al profesor Iman por su tiempo, por su disponibilidad de la Universidad de Sheffield en el Reino Unido. Además, son las 10 de la noche en este momento en el Reino Unido y pues bueno, ahí se está tomando un buen café para que nos acompañen. Muchísimas gracias. Contarles un poco de IABSE antes de darle paso al profesor. IABSE, la misión que tenemos en IABSE y es parte de lo que estamos haciendo es intercambiar, es el intercambio de conocimiento, ¿cierto? El avance en la práctica de la ingeniería sísmica y la ingeniería estructural, no solamente en edificaciones, sino también en puentes alrededor de todo el mundo. Así que tratamos aspectos de la ingeniería estructural, de diferentes materiales, tipos de estructuras, también de procesos constructivos. Estamos todo el tiempo trabajando y desarrollando y compartiendo conocimiento alrededor de esto. Básicamente toda esta misión la logramos con 5 actividades, ¿cierto?, principales, aunque obviamente hacemos muchas más, pero tenemos conferencias, congresos, seminarios, tenemos diferentes estados y tamaños de reuniones académicas, tenemos diferentes publicaciones técnicas, tenemos una gran gama de premios relacionados con ingeniería estructural. Desarrollamos grupos técnicos donde el profesor Iman pertenece y se hacen documentos y estudios de caso, y tenemos también programas para los jóvenes, para ustedes estudiantes que están terminando, que están subiendo sus carreras o que recién también empiezan su vida profesional, para que se unan y obtengan todos los beneficios de la asociación. Es una asociación que tiene casi ya 100 años, nació en 1929 y se han venido haciendo visitas de campo, dado que ha estado muy enfocado en lo que es en Europa. Es una asociación que nació en Suiza. Entonces, pues por este lado del mundo su presencia ha sido menor, pero estamos trabajando fuertemente junto con otros grupos nacionales de cambiar un poco y acercar esa IABSE internacional también a nuestro país, y que podamos tener desde la ingeniería colombiana tanto los aportes que podamos dar también como los beneficios que podamos tener. Tenemos una red latinoamericana, hay algunos grupos nacionales conformados donde nos reunimos. Hace poco estuvimos haciendo una visita de campo en un aeropuerto internacional en la Ciudad de México, nuevo, ¿cierto? Que se está haciendo con unos sistemas de protección muy importantes. Hacemos diferentes actividades relacionadas y tratamos de llevar IABSE y todos los beneficios por estas partes del mundo. IABSE es redes humanas, es compartir conocimiento, es compartir experiencias con amigos, con profesionales, para que sigamos creciendo como personas y creciendo también profesionalmente. Vamos a todos los eventos que se hacen, tenemos una cantidad de eventos, ¿cierto?, organizados por IABSE Internacional, y cada grupo nacional también tiene su autonomía en generar eventos o diferentes aspectos técnicos, que es lo que nos está convocando hoy. Nuevamente le agradezco a la Universidad del Norte. Tenemos casi 3.000 miembros alrededor de todo el mundo y más de 52 grupos nacionales en el mundo trabajando dentro de la asociación. Es una asociación bastante fuerte en la ingeniería estructural. Algunos ejemplos de los eventos que se hicieron el año pasado y el año antepasado. Se siguieron haciendo eventos a pesar de la pandemia, ya muchos online, ya se retomaron algunos eventos de forma física. Tenemos diferentes webinars alrededor de diferentes también temarios de la ingeniería que se llevan, generalmente son hechos en inglés, pero pues o conducidos en inglés. Por eso nosotros desde los grupos colombianos de la red latinoamericana estamos promoviendo ya también conferencias en español. Sin embargo, es bueno que cada vez nos vayamos acercando también al idioma inglés para poder obtener todos los beneficios y esa red humana y de contactos con otros ingenieros. Vienen otros eventos como el Simposio en Praga 2022, viene también el Congreso en Nanjing en el 22 también. Hay diferentes congresos que van pasando. Cada grupo nacional a veces hace congresos, pero están los simposios, que son los eventos más grandes de la asociación como tal. Tenemos diferentes publicaciones, tenemos el Journal Structural Engineering International, tenemos libros de casos de estudios, tenemos Structural Engineering Documents, que todos son documentos técnicos que están a disposición, que están ahí al alcance para nuestra ingeniería estructural y para mejorar nuestro conocimiento y aprender de todos los casos que se han evaluado en todo el mundo, básicamente, pues, o muy enfocados también en Europa. Tenemos un programa muy interesante para jóvenes ingenieros, que son para personas menores de 35, algunos de ellos ya pasamos por aquí, ya pasamos y arrancamos por aquí y ya seguimos. Fue una experiencia muy interesante cuando estaba en ese grupo, y tiene unos beneficios en cuanto a tarifas, en cuanto a programas especiales, que solamente son para un grupo, pues, de personas menores a 35. Entonces, los animo a que también miren, ¿cierto? En la página, revisen todo lo que IABSE les puede ofrecer, que de verdad es bastante interesante. También hay una membresía tipo estudiantil. Esa es para menores de 27 años, es muy económica, solo vale, pues, bueno, solo va a cambiar, vale 20 francos, alrededor de unos 80.000, 90.000 pesos al año, y pueden tener acceso a a todos los beneficios realmente de la asociación. Obviamente tendrá algunas restricciones, pero vale la pena también empezar por ahí si estamos estudiando en este momento. Entonces, ¿por qué vincularse con IABSE? Es una comunidad global, realmente en todo el mundo tenemos presencia, como les decía, más enfocado en Europa, pero cada vez lo estamos acercando más por estos lados. Todos los beneficios, vamos a tomar parte de los congresos, de los eventos, a estar con el estado en arte de la ingeniería estructural, como les decía, no solamente en puentes, que por su nombre lo dice así, sino también en edificaciones. Cada vez ha venido más entrando en parte de edificaciones, y finalmente todo lo hacemos para hacer una diferencia, ¿cierto? En cuanto a cómo hacemos nuestra ingeniería estructural. Desde el 2019 se reactivó el grupo colombiano. Él existe hace muchos años, pero estuvo quieto un tiempo. Aquí estamos los que estamos en el comité ejecutivo. Aquí en la foto aparecemos. Yo soy el presidente, Nelson Betancourt, el vicepresidente, y tesorero y secretario Alfredo y Luis David, que son ingenieros que estamos trabajando por el grupo colombiano en sacarlo adelante. Una de las actividades que desarrollamos, ¿cierto? Es la iniciativa BST, que ya les voy a contar sobre esto. Al momento en Colombia somos 23 miembros, hacemos parte de IABSE Internacional, pero por ser parte de IABSE Internacional, inmediatamente somos parte del grupo colombiano, y esa es más o menos la distribución de los miembros que tenemos al momento. Somos pocos miembros en Colombia, pero pues estamos trabajando para crecer. Entonces, les decía que en el 2020, más o menos, empezamos con una iniciativa que se llama la BST o la BST, que es Puentes para Transformación Social. ¿Por qué lo quisimos hacer? Porque queríamos llegarle a todos los diferentes lugares del país transmitiendo conocimiento. Ese intercambio de conocimiento, ¿cierto? Conexiones de conocimiento, como lo dice la imagen, es lo que estamos buscando. Queremos que el conocimiento de ingeniería estructural de expertos, como en este caso el profesor Iman, que nos acompaña de IABSE Internacional, y dentro de 15 días que tendremos también los conocimientos del profesor Jorge, que esos conocimientos no se queden solamente en algunos sitios, sino que podamos llevarlos a diferentes sitios del país. Ese es el foco principal y la misión que nosotros queremos con esta iniciativa BST, es impactar, ¿cierto?, positivamente en esa transformación educativa en Colombia. De ahí nació la iniciativa, y tiene dos etapas. Está la fase 1, que es la que estamos nosotros en este momento, que es una conexión, un intercambio del conocimiento teórico, es decir, el grupo IABSE con sus expertos y se va a universidades. Estamos empezando con las universidades de mayor reconocimiento en el país, pero poco a poco seguimos yendo, ganando experiencia en esta iniciativa, en esta actividad, y nos iremos yendo hacia otras regiones, hacia la provincia, para que todo el país en todo el país podamos tener este tipo de actividades. Después viene la fase 2, que es una vez tengamos consolidado también esas relaciones con diferentes universidades, con diferente academia, y de hecho queremos llegar hasta los colegios mucho más adelante, es generar unas brigadas de acción donde junto con los expertos podamos colaborar, o podamos ayudar a solucionar problemas de ingeniería sencillas de pronto a regiones o a provincias que no tienen no tienen el acceso pues a los ingenieros, que nosotros podamos dar recomendaciones para que pues, podamos generar un beneficio, ¿cierto?, a la comunidad. Entonces, esas son las dos fases de la iniciativa. Estamos en la fase 1, que arrancamos realmente pues el año pasado después de toda la pandemia. Así que tenemos los expertos de IABSE, los profesores de la academia, toda la comunidad estudiantil y toda la comunidad en general, porque vamos a tener pues también estos eventos. Hoy es privado y vamos a tener un evento abierto al público. Entonces, como les decía, son dos eventos. Hoy es una cátedra. Queremos compartir con ustedes las experiencias del profesor Iman para que ustedes tengan una interacción con alguien de mucha presencia, de mucha relevancia y mucho conocimiento, para que aprovechen y les hagan preguntas, en cualquier momento lo interrumpen, pues todo muy coordinado para que se pueda alcanzar los objetivos de aprendizaje. Y dentro de 15 días vamos a tener un webinar donde ya es abierto al público y lo haremos en compañía del profesor Archie. Finalmente, en la fase 2 haremos mesas de trabajo con la comunidad para poder dar solución a problemas relacionados con la ingeniería estructural, pero pues ese vendrá más adelante. Muchísimas gracias a la Universidad del Norte, muchísimas gracias al profesor Iman por su tiempo, a ustedes estudiantes por el tiempo también. Entonces los invitamos a que sean parte de la familia IABSE, que entren al grupo colombiano y obviamente a escuchar la cátedra magistral del profesor Iman. Antes de terminar, él es profesor asociado en Ingeniería Estructural y líder del grupo de Ingeniería Sísmica de la Universidad de Sheffield en el Reino Unido. Tiene más de 20 años de experiencia en investigación, en consultoría, en los campos de ingeniería sísmica, diseño basado en desempeño, dispositivos de disipación de energía, optimización estructural y técnicas novedosas de reforzamiento. De hecho, aquí vamos a hablar de diseño basado en desempeño, y entre 15 días hablaremos también de diseño basado en desempeño, pero orientados a elementos de disipación de energía que cada vez coge más fuerza en nuestro país. Es miembro de diferentes comités técnicos y redes de investigación nacional e internacional. Está en el grupo de trabajo 6.6 del FIF, rehabilitación de estructuras prefabricadas en áreas sísmicas, del grupo de trabajo 7.6 del FIP sobre estructuras resilientes, y del grupo de trabajo 1.1 de IABSE, que es nuestro experto, como la mejora de la resiliencia sísmica en estructuras de concreto. Así que todos estos temas ha trabajado el profesor IABSE, profesor Iman, y también es editor asociado en varias revistas importantes a nivel internacional. Así que tenemos el honor de tenerlo hoy con nosotros. Y bueno, así que para adelante, en este momento le voy a dar paso al profesor Iman. Profesor Iman, I have finished. So,
thank you very much.
Señor. Hola, Jorge.
Hola, no, muchas gracias por tu presentación. Una preguntita. Sí. Pues nos vendiste el cuento, pero ¿y si nos interesa cómo te contactamos? O mejor dicho, cómo, en caso de que hayan interesados, nos mandan un enlace o algo para quedar en contacto.
Listo, cuenta con eso, yo te lo mando y entonces se lo mandamos a todos los estudiantes.
Sí,
vale. A ti. Bueno. Okay, I'm gonna stop sharing my screen.
Perfect. Shall I start?
Jorge, ¿cierto que sí? Yeah, Professor. Yeah, try.
Yes.
Yeah, whenever you want.
Okay, perfect. Thank you very much for the very nice introduction. And now I have a copy of my CV in Spanish as well. That's great. And thank you. So I hope that you can see my screen.
Yes.
Yes. Perfect.
Yes, Professor. Yeah.
Perfect. So First of all, thank you very much for your invitation. It is really my pleasure to have the opportunity to give this presentations to you, and it is really nice to meet you, however, virtually. In this talk today, I will speak about some new developments in the performance-based design, seismic design, and a little bit of optimization. And in the next talk that I have in 2 weeks' time, I will focus on the optimization based on the performance. So they will be complementary topics. To make everything easier for you to understand, I present my lecture in 4 different sections. I will be careful about the time, so I finish exactly at 6 o'clock your time, because I know it's already late there as well. So I start with the concepts of seismic design, the normal design process, what nowadays we do if we want to design a building, a structure. This part of the lecture starts with a short introduction. I'll talk a little bit about the ductility, seismic design, and different types of analysis, the way that we analyze the buildings. I don't talk about the Eurocode 8 for you. I show very quickly a practical example, and I finish this part and go to the next part. This picture here, I'm sure you have seen pictures like this a lot. What I want to say is that we all know the earthquake is serious. If we do not design our buildings properly for earthquake events, that's the consequence. That's what will happen. Yes? Now, today we try to discuss with each other what are the ways that we currently design, what are the problems or limitations, and how we can address some of them by looking at the performance-based design concept. And in the last part of the presentation, we talk more about how we can use it for more efficient design of buildings. We know that this picture is from Kocaeli earthquake in Turkey in 1999. See that what the earthquake has done to the buildings. And I always tell my students, look at these buildings, this building here and this building here. They look similar, yes? I think they were almost similar buildings. This one is completely destroyed, while this one, at least it did not collapse. You see here, extensively damaged. The reason for this is sometimes the detailing that they considered during the design and also construction. So what is important for me is that the earthquake, we know it's an excitation of the ground. It leads to damage to both structural and non-structural elements. And if we do not design our buildings, they will collapse like this. So definitely this is not what we are looking for. The problem historically is that the earthquake forces are huge. If we look at the other forces that are applied to the structures like wind load or dead load, we'll realize that even in the worst case scenario, the earthquake elastic forces are up to 10 times higher than wind. It means that we need to find a way to deal with earthquakes. We cannot just design our buildings like the other types of loads for a load that is that much strong. So how can we deal with this idea? There are different ways. One is to isolate our buildings. This is base isolation systems that are widely used in some countries. It is not in the scope of my talk, while I'm very interested in that area as well. The other one is that to increase the damping, absorb this energy by using energy dissipation devices. Again, this is not the topic of this talk. Actually, in my next presentation, I will focus on this. But in normal circumstances, normal buildings, what we do is that we say, building, we want to design them against a load that it is really strong. So we accept some level of damage. We accept that some part of our building will be inelastic. And what we do is that we control this damage in a way that it is in the locations that we want. It does not lead to basically harm people, injure people, kill people. And it will be restricted to the limits that we want. So that's the whole idea of seismic design. Now, my point is that conventional design methods cannot really control this accurately, but with the performance-based design, we can control this concept. So concept is the same. It is the details that basically we apply this concept for the design. When we accept the damage, it means that the building will not be elastic. You know from your undergraduate modules, this is the load displacement graph. So vertical axis load, and this is displacement. For a linear system, it's a blue line. For the nonlinear system, all buildings in the reality is the green line. So they reach the yielding point and then they yield. So they experience higher displacements. The definition of ductility is the maximum displacement that the system can accept divided by the yield displacement, the displacement that the load displacement diagram changes, like here. So this is the yield displacement, and this is the ultimate. So this one divided by this one, as is written here, is ductility. So we can assume that the area below these two curves is equal. It is the energy that the system absorbs, and it makes this possible to have some design equations. It's not in the scope of my module, this talk, but it's something that you can continue looking at. Now, this slide is very interesting. I look at the load displacement of curve. If the system is elastic, this is the red curve. Everything would be elastic. But this is the load that we need to design our buildings with. It's very high. It means that the building will be very strong, large sections, a lot of reinforcement, for example, or large sections. It's not possible. If we accept nonlinear behavior, if we accept damage, it means that instead of this load, we can design it with this load, much less, half of that. Yes, it's good because the structure would be lighter, less material. It means that basically the idea is that I can make the structure weak, but accept some level of damage. And I can continue doing this until I reach this purple line. At this line, if the structure is weaker, the structure will collapse, will completely damage. So what we do in seismic design practically is that we select a line that is above the minimum threshold. And we say that instead of designing with this FE, that is elastic load, you can design it by a load that is much less than FE. It is FE divided by R, that is R is the behavior factor. We have it in all seismic design guidelines. So practically the message is you have the load, divide by a factor that is generally 6, 8, even 10. You reduce the load, you design it, and you hope that the damage would be acceptable. But can we guarantee that? No, because normal design doesn't give us the tools to be able to do that. Now, this is not that much important. I'll go to the different methods that we use for a design of buildings to calculate the loads in elements. We have it in all design methods. First one is a linear static procedure. I explained about that. Then linear dynamic procedure, that it's by itself, it can be response spectrum method or time history. And nowadays in performance-based design method, we use nonlinear static. Again, I explained about what does it mean. And the most accurate one is nonlinear dynamic. So I go through them very quickly, and I tell you that what is the differences between them and what are the advantages and disadvantages. Now, linear elastic. Linear elastic means that I apply the basically load as an seismic load as an equivalent load. It generally assumes that the first mode of vibration is dominant. And the structure is elastic. So basically it's telling us it is not very good for tall buildings because the effect of higher modes would be dominant. I'll show you how does it work. This is the building, and this is the way that we distribute the load. Yeah. So we say that this is the earthquake, ground vibration. We distribute it. Here we distribute it generally with an equation or linear, and then we analyze it. From now on, the the earthquake load is like wind load, any load that is applied laterally, and you can do it with any software or hand calculation and design. But we know that the effect of hard modes are not considered. So codes, they suggest a better design method, response spectrum. What does it say? You have the response spectrum of your earthquake. This is for your location. For example, for Colombia, I'm sure in your seismic design guidelines, you have it for different regions. You know the period of the vibration modes for your structure. You do a modal analysis. You find the response for each mode, and you combine them. Again, a structure is elastic. It means that you assume there is no damage in the building. So practically, you have to reduce the load. So here is the first mode of vibration. I find the response. Here is the second mode of vibration. I find the response. Here is the third mode of vibration. I find the response. And then I combine these three by using a method like SRSS or CQC very easily. But a more sophisticated elastic analysis is to apply the seismic load and perform time history method, linear dynamic analysis. So I show it again. So it means that you solve the dynamic equations directly. If you had the structural dynamics, you'd have heard the Duhamel integral. If you don't know, that's absolutely fine. The equations of motions will be solved directly. This is good because the analysis is more accurate. The effect of higher modes are considered. This is bad because you need an earthquake instead of response. And for seismic design, we are not sure what would be the next earthquake. Do we know? We don't know what would be exactly the next earthquake record. So this will be challenging. Which earthquake record I have to use for design? Yes. And also still the structure is elastic. So the seismic design codes, the performance-based design codes, they started as thinking of a method that is easy to do, but also is more accurate. We want to know the behavior of the structures when they are nonlinear, when we have damage. So what we do is that they basically propose pushover analysis or inelastic, basically a static analysis. What does it say? It says that you apply a load to the structure, like this load. The total of these black lines is the red line. Increase the load gradually, yeah, increase it step by step, and at each step, calculate the total load, that's the red line, versus the basically the roof displacement here, the target. And you have a curve like this. This curve basically tells you what is the behavior of the structure. The initial line is the stiffness of the building. Here is the capacity of the building, and you can see how the building damages. So you have the failure mechanism. You can calculate it to estimate the response of the structure or even the ductility of the system. So you have a load, you push a structure step by step, and you find the response. Now, the elements are basically modeled in an inelastic way. If the elements are elastic, the response is like this. This is the force displacement is a line. This is elastic, yeah, in the previous methods. But in reality, we know that if we have an element, this is the response of the element, okay, under the load, cyclic load. And basically what we do is that we understand when the system is cyclic, we have reduce in the capacity and stiffness. They call it degradation. It means that the elements are damaged eventually, and in the end, they will be completely damaged. The good thing about nonlinear pushover analysis is that we can model this. Basically, we can model the degradation, the damage in the building, so the behavior is more accurate. How do they do this? That's clever. These red lines, these black lines are the hysteretic response, load displacement of the cyclic load. And they find this red one. I spent a lot of time to draw this red line, okay? I hope that you like it. I show it again, yeah? This red line, basically this is the envelope of the response, backbone curve. So instead of the black line, they use the red line in the analysis. And it makes everything very easy. everything would be much easier. What is the advantages of this? This method helps us to find the maximum shear capacity of the structure, to tell us what is the failure of the mechanism, tell us that how the plastic rotation form, and even ductility of the system, or even it helps us to basically estimate the damage in the building. I'll give you an example. Oh, sorry. This is the limitations. What are the limitations of this method? The limitations is that still it looks at the first mode of vibration. It means that the effect of higher modes are not considered. If you look at the 3D systems that they have torsion, they are irregular buildings like this one, it is bad. It can't really work very well. There are methods to address these issues, but still those methods are not very accurate, and they are under progress. So these methods are generally, pushover is generally good, I would say better for a 2D system when it's regular. An example, okay? Let's work together. This is the building, and we apply a lateral load here, and we start pushing the building from left to right. I push the building a little bit. At the first push, when I get a little bit further, these are the plastic hinges in the beams. Yes, these are the plastic hinges in the column here base and in the beams. Basically, it shows the location of the damage. Yeah, I push a little bit more. These hinges are increasing, so we have more damage in the structure. I push it more damage, and I continue doing this until I reach the last stage. I wish I was using my tablet, I could draw a line, but I reached this stage, and this stage, the structure basically reached the mechanism behavior. What does it mean? It means that it fails, it falls over, it collapses. Now, we know that this displacement, roof displacement, when this displacement reaches around 40 centimeters, the structure will collapse. So I know the capacity of the structure. I know that here, look at these locations. The plastic hinges, the damages are in the beams. Agree? I can see you on the video. Do you see any plastic hinge on the columns? If you see any plastic hinge on the columns, please raise your hand. I see if you raise your hand. Do you see any damage on the columns? Yes, one of you says yes or no. Do you see damage on the columns? If you look carefully, we see damage in the columns here, yes, here, here, and here. But this is the base. That's okay. So basically, what we have here is the mechanism of the failure is good. This structure was designed properly. The plastic hinges were all in the beams, not in the columns. Perfect. So actually, this is a good design, and this pushover analysis provides us with a lot of information. We get back to that more. This is the structure. This is the load that we apply. We increase the load, and at each step, we calculate the roof displacement. Is what just said. I said, and we draw the curve. Vertical axis. This is the total force or base shear. This is this V, vertical axis, and horizontal axis is displacement, is UR, and the blue line is the real behavior of the structure. I can, from this behavior, understand what is happening in the building. For example, here at this displacement or force, I have the first damage because the stiffness changed. Here, the structure is heavily damaged. Here, the structure is almost gone, is collapsed. So basically, by doing pushover analysis, I can find a way to find basically the overall response of the system. But the codes tells us that when you do the pushover analysis, you need to choose a lateral load here, F1, F2, F3, F4, F5. How do you distribute it? It's up to you. You can use similar loads, you can use triangular, modal, and unfortunately, the final response depends on the type of the load that you consider. So to help with that, codes, they say that you have to choose at least 2 key loads. One, you have to choose the uniform, and the another one, choose one of these 3 and analyze the building and find the worst case, find which one leads to the higher forces. So basically, you have to perform two pushover analyses, one for the uniform load and one for one of these, triangular, modal, or combination of the modes. In the course, it is well explained. I don't want to spend more time on that. This is the equations of the same thing that I said here, nothing more. It just gives you an idea how these loads are distributed. Now, I have an example. I asked one of my students, like you that are sitting here, to perform pushover analysis using three loads. This uniform load, this uniform is this one, okay? Then this is, sorry, this triangular load, this triangular load, okay? This is this one, triangular. And then this is mode one, this is this one. So basically using this one, and this one, we want to compare the results. If we do that, we realize that this is the load displacement curve. We realize that the stiffness of the system was similar. So this load pattern didn't change our idea about the stiffness. We realized that the capacity for these two loads is the same. For this load is different. That's important, really important. Why? Because if you use a wrong load, the capacity that you estimate would be completely different. It's dangerous. Yeah. So for the stiffness, they are all the same. For capacity, they are not. So it's important. That's the reason you understand. Code says that use all this, one from here, one from here, and look at the maximum, because your response will be between this line and this line. So if you realize, I just said, code says that use uniform and one of these two. And code is right, because these two are very similar, and one of them would be enough. Now, the last type of analysis is nonlinear dynamic analysis. It means that you apply the earthquake on the building, model the building accurately nonlinear, and run it. Yep. In this case, you have
wait for a minute, please.
Can you hear me? Sorry.
Sorry, for whatever reason, the computer shut down. Can you give us like a couple minutes while I restart?
Sure. I wait.
Sorry.
Yeah, Professor, technical problems you can never escape from.
Always. Believe me, I'm get used to that all the time, especially with this online presentations.
Yeah, exactly. So yeah, I don't know what happened here.
No, we'll wait, and it's fine. I will focus on the more important parts that the students like, and go faster on the more equation, these things.
But nice though. The summary you are doing, very important, because we need to understand clearly what to expect from a different seismic analysis methods.
Exactly.
What can we do with that?
It's
we
true,
can do
especially because
for
the performance, we just use the last two, so we can't really practically use any of the first two. While in the normal design, we always those ones are the one that we use.
Exactly.
My students generally a little bit confused about pushover because it's the first time they hear. Most of it is the case for your students as well. But when they hear something later on, when they read, they understand. You know, I think at this level, what I say, give them a flavor of what they have to do, and then hopefully when it's time and they go deep, they understand the details.
Yeah, perfect. Yes.
So you realize when the computer is back, yes?
The what?
When the problem solved, you will realize, yes? You will tell me, because I
yes, of course. Yes, Professor. Yeah, we have here in WhatsApp, we have a chat.
Oh, okay.
And yeah, they are reviewing the system.
Give us 5 minutes and we almost are solving the problem.
Ok. Listo, Melissa, gracias. Sí, no hay problema. Si me escuchas, Jorge, Melissa, no hay problema. Muchas gracias. Ahí vamos a ir esperando que se reinicie.
Okay, we are back.
Sorry, I don't know what happened. Can you hear us?
Yes, I can hear you clearly. These things are absolutely normal, believe me.
Thank you very much.
Yes,
Professor,
okay.
for understanding.
So, shall I continue? Can you hear me now? Perfect. So, I was saying that pushover analysis, that we will use it later on, is good, but the problem is that it depends on the lateral load that we use. And that's the reason code says that use uniform, the red one, and either of these two, and use the maximum response. So the actual response will be between these two. I will get back to that. The nonlinear dynamic analysis means that I have my model accurate, everything is nonlinear, and then basically I apply the seismic load and analyze it. The problems are, first of all, if we want to do that, we have to model the structure in an inelastic way, and we need a lot of information about parameters and the elements. And also, we need to have the earthquake. I told you, we can't predict what would be the next earthquake. There are methods for this. I use it a lot for my research, synthetic earthquakes, but there are problems with them. So I told you we need to know the details for this. This is, for example, left-hand side is the cyclic behavior of steel. Then this elastic is easy. Now you have to know exactly the response of the material. Right-hand side is the behavior of concrete. So if you want to model in a nonlinear dynamic analysis, it is very difficult because you have to know exactly the parameters for your structure. I skipped this part. It's a Eurocode, and I show you an example to show how accurate you can predict the response of the structures. Okay, this is the building that we tested on a shaking table in France. We were leading the project from Sheffield, and it was it's the largest shaking table in Europe. So this is a full-scale building, 2-story, reinforced concrete, RC building, and this is the detail. So we did the test, and we realized that during the test, we increased the acceleration of the floor, the PGA. We realized that first, we have damage here at the, as I said here, on the joints on the first story, horizontal cracks. Then at the higher PGA level, we had cracks at the base. And then after reaching the maximum design, basically we had complete or deep damages here again, as you see on the first story column. So we had the damage pattern. Now, I asked one of my students to model the structure. We used Brain 3D software. Nowadays, my students, they use OpenSys, but at the time they used Brain 3D, and this shows how they model the structure. I don't go through the details. And this is the material property. So we had tests. This is the behavior of the concrete. So that our concrete was relatively weak because it was the representative of a bad structure. So it shows the behavior of the concrete under compression this side, and this is the behavior of the concrete under tension. So accurate model. Load, it's a stress strain response. This is the bond slip behavior. It means that when the reinforcement and concrete, they move, when my pen is the reinforcement inside the concrete, it starts sliding, bond slip behavior. We model that. We have code for this. And this is the gap properties. In the connections, you saw that the connection was damaged. So the connections, they open and close. So basically, this gap properties for that. You see how difficult it is to consider all of them. Then I asked my student to use pushover, and she actually used a pushover with a triangular load. It's a uniform load. It's a triangular load, and it's the basically plastic hinges. She told me if I do this, the first plastic hinge is here, second plastic hinge here, third one here, fourth, fifth. And we looked at the damage here. It was different. It was different. So I told her it is not acceptable. I don't like this distribution. So she did another one. She put those the same, and now she told me, oh, the plastic hinge starts from here, then here, then here, then here, then here, then here. Again, it's not with what we observed in the test. So I told her it is not acceptable. And if you look at the load displacement, the first yield and the collapse are very different in two cases. So she analyzed for very different combinations for me. This is the different combinations. And she looked at the type of the damage and the capacity that she gets from those. You see, the capacity of the system is different. It depends on the load that we do with pushover, and that's bad. I realized that actually the answer was this one, the best answer. Something between the two loads that the code asks us to consider. And here, the best answer. So if you do 1 force here and 1.5 times the force here, something that is not in the code, you realize that the order of the damage would be more reasonable. Well, damage here, damage here, damage here. So it's very close to what we saw in the basically tests. Then we perform nonlinear dynamic analysis. This is the test in the shaking table, the blue lines. And this is the pushover. When we push the structure, you realize that the answer of the pushover analysis, it's like an envelope, backbone of the cyclic. So to give you an idea, because I use pushover later on for performance-based design, pushover gives you an envelope of what is happening during an earthquake. It's an easy method, is accurate enough, and is much simpler than nonlinear dynamic analysis. Now, I asked my students to perform nonlinear dynamic analysis. You can see here the response of the structure, the actual response is the red line. Yeah. And the blue one is the one that our model gave us. And you see at different PGA levels, first story, second story. We published these results. You can look at my papers. You will see the agreement is great. So my models on the structure could predict the behavior of the structure with a very good level of accuracy. Accurately could predict. So these models, nonlinear dynamic analysis, can be very accurate. What is the problem? I told you, you need to have detailed information of the material and also the earthquake, something that we don't have. So these are the methods that we use for conventional design, seismic design. The elastic ones, the first two, are not really used for performance-based. The second and the third, pushover analysis and nonlinear, they are more accurate. They consider the real behavior of the structure, and they are the methods that can tell us what is really happening in the building, so we can use it for design purposes. We go to the next stage next step of my presentation, ductility-based design. Ductility-based design is relatively complex. You have my videos. If you want to have a copy of my lecture notes, I'm more than happy to share with you. But because we had some delay, this part I go faster, okay? I don't teach you the details. This is very interesting, but it's a little bit advanced. It's more for the MSc and PhD students. If you like, you can even contact me later and ask your questions. So don't panic if you don't understand well. So I start with the definition of the ductility, and then I go focus on the behavior of the system based on the ductility design. The concept of ductility design means that this is important because I use it in performance-based design. It says that I am happy to accept the damage. We cannot basically assume the buildings that remain in the elastic range and the large earthquakes. Why? If you want to design a building to remain elastic in large earthquakes, you have to use large sections, very strong sections. I don't know, columns 3 meters by 3 meters. Yes, a lot of reinforcement. It's not economic. We can't use that. So what we do, I start at the start of my presentation. We accept damage. We accept damage, but in a controlled way. But what is the problem of damage? When I have the damage, I may have basically reduction in the capacity of the building. How can I control it? With ductility. I said that some buildings, they can accept a lot of damage. Some buildings, they cannot accept a lot of damage. So I have to control the damage in a way that the building does not collapse. The parameter that helps me to control the damage, the parameter that helps me to control the response of the structure is ductility. So that's the whole idea. There are some key design factors. Remember these ones. Plastic hinges should fall in the beams before columns. So I want to plastic hinges in the beams, not columns. Do you know why? Do you know why we don't want plastic hinges in the columns? We want in the beams. If you know, you can even answer in Spanish. Someone translates it to me. Can you tell me? Anyone? Why we don't want plastic hinges in columns? It says bad. Plastic hinge in column, bad. Why is bad?
Si escuchan todos bien allá, ¿cierto? Si alguno quiere hacer un comentario o si quiere contestar al profesor, levanta la mano. ¿Por qué no se deben tener?
Señor, ¿dónde queremos que planifiquen que hayan problemas en las vigas o en las columnas? ¿Alguien lo puede decir en inglés? No, sale Daniel.
We want the plastic hinge in the beams because with that we avoid to a soft story that's a great problem.
Okay, it can be, yes, it is towards the direction that I want. Thank you very much for answering. When we have damage in the columns, plastic hinges, the columns collapse, yes? If the columns collapse, the whole building goes down. So we don't want to have damage in columns. In beams is okay because a part of the building will be damaged. So basically for gravity load, vertical load, we have to protect columns, and that's the whole idea. Thanks. So we need to provide confinement in the material because in the design, because we want to have ductile. If we don't have confinement, if we do not have shear links, close shear links, the connections or plastic hinge zones, they damage quickly. Is not acceptable. We don't want the connections to be damaged. We want the structure to, the damage will be far from connections. Why? Damage in the connections, the structure fall. Yes, it's dangerous. And shear failure is very bad. Shear failure is brittle. Shear failure happens suddenly, quickly. So what we want is that we prevent shear failure as well. So again, these are the whole ideas that we have it in ductility design and then in performance-based design. So it's very important. I don't go through the details of the ductility design that much, just I explain that based on the ductility of the system, we reduce the load and we rely on the nonlinear response of the structure. And it's important to consider all of these points to ensure the structure will survive, will not collapse. I use the same idea of the ductility. Ductility is the maximum displacement divided by the yield displacement. This is the one. I just explained that the area below the elastic and inelastic system can be equal. And if you do that, you can find very simple equations. I'm sure my students, they hate it when I say simple because they are not simple. You can have some equations that relate these parameters to each other. You are lucky that I'm not going to spend time on that, and I'm not going to ask an exam question from you. So very quickly, the whole idea, as I said, I don't have time to go through it in detail. I'll just give you a flavor of that. They look at the response spectrum. This comes from the code, like the Colombian code, okay? Then they change it to the response of the acceleration versus displacement. It's very easy. An Excel file can do that. And generally, we use the simple equation that the displacement spectrum is the acceleration spectrum over the omega, that omega is the 2 pi over t period of the building, is the frequency of the system. So I change it to this one. Then I add the inelastic to the elastic behavior. How? There are different methods. I generally suggest a very simple one. You divide the elastic system, the response, the blue line here, by a factor. That is, factor is expressed by this equation. It is 1, then it reaches up to the ductility. I will show you later on. And based on this ductility of the target, ductility 2 means that almost brittle. Ductility 4 means that medium ductility level. Ductility 6, 8 means that the building is very ductile. For example, if you have a reinforced concrete frame that you have very good links, it's ductile, is this one, it's ductility 6. But if you have a reinforced concrete frame that it does not have shear links properly, the material is bad, you can't really accept ductility 6 or 4. You go for ductility 2. And in that case, basically, just you divide it by this equation and you get the inelastic response. So it is this one. And this inelastic, this is the equation that I used to change the elastic response, the blue one, to the inelastic response. And this is as the simple equation that I told you here. This is that equation. If you read the notes, you will realize. So basically, the red one is the blue one on the top divided by this blue. And each point, when you divide it, you get the red one. The red one is the behavior of the structure that is inelastic, the actual behavior of the structure. Now, if I want to know basically what is the response?
Can you wait again a minute, please?
Oh, again disconnected. Yes.
I'm having problems again. We don't know what's happening, so give us 5 minutes, please.
Sure, I'll wait.
I'm so sorry again, Professor Iman.
No, it's okay. I promise I'll finish on time, so don't be worried. And the presentation it gets nicer, more pictures and colorful. And
no, but it's very nice. It's going very well. Thank you very much.
Thank you.
Yeah, I don't know what's happening. Probably not only the computer, but also the video beam, the projector is, you know, with an issue. I don't know what's happening there. Maybe a short circuit or something like that. I don't know what the circuits.
Yeah, we were thinking to give them a break, so it is a break for them.
yeah, we can think of this as a break.
Exactly, a break, yes.
a coffee break.
Exactly, coffee break, yes. For me, because it's too late, I went for the decaf tea instead of
exactly.
coffee. I had to sleep after that, yes.
Exactly, not coffee at 11.
No, 11. I can't go for coffee, no.
Well, but in my case, I can drink as many cups as I want, no matter the time, and I can fall asleep immediately.
Well. Really,
no
good.
problem.
At night, no, but I generally drink, let's say, 6 to 8 cups of coffee per day.
Okay,
but not anything after 4. So after 4, I stop. 4 p.m. No coffee. Otherwise, I can't sleep.
Yeah, some people live in 1 cup in a whole day. If they drink it
they can't sleep. It's true.
Yeah, they can't sleep. Yeah.
Actually, my colleague was exactly saying this morning. Yeah. I was thinking this is an international word. So I'm talking to you guys this side of the world. Tomorrow early morning, I have meeting with my PhD student in New Zealand. So completely other side. So
that's cool.
Yes, exactly. That's the advantages of the technology, you know.
Yeah, you are in the middle, very far to the east, to the west.
Exactly. So actually, yes, UK is in good place for this aspect. Time-wise, you can be both. Yeah.
Exactly. Nice.
Yes.
Yeah, that's a good thing. Exactly.
Yes,
otherwise impossible.
It's impossible. Yes. I saw a lot of nice, friendly faces on your presentation, and I missed the time that we had the opportunity to travel, and yes, for me, for my next travel, actually after 2 years, it will be next week. I have to go to Milan for a PhD project. I'm external examiner. But yes, cool. Like 2 years that I've never, I didn't have a chance to travel because of COVID.
Yeah, well, 2 years is
Yeah, I mean,
it's not so much, but
but
it's long anyway.
Yes, it's true.
Yeah, last time I went to IABSE event it was in London. It was really? 2011. Okay. No, 2011, right? 2011.
Yeah, I think
2011.
So. Yes.
That was the last time. I mean, 10 years ago.
Wow. So
I had just came from Japan. To Colombia. I had just came here and then I traveled to.
I've never been in Japan. Actually, it's a place that I would like to go.
In Japan, it was nice. I stayed there for 5 years and a half.
Oh,
and it was a
really?
It was a very great experience there.
Actually, I'm thinking for my sabbatical next year I go to Japan. Yeah, but I have to do some paperwork. Yes, Japan is very nice.
Yeah, it's very nice. It's very nice. And if you work on performance-based design and energy spacing devices, it's very nice there. Yeah, exactly.
Yes.
That's what I studied there. Yeah, that's what I studied there.
Okay, so it was your area as well. Okay.
Exactly. Yeah, that is. We're back on business.
We are back exactly.
Hi, can you hear us?
Yes, and I think you had your coffee break. Yes.
Yeah, so we actually had to connect my laptop.
So hopefully this time is safe, yes?
Yeah.
But they can see me or not on the larger screen? They can see the presentation?
Yeah, we can see you and everything. We just don't have that other camera, but yeah, we're good.
Fine. If they can see the screen, that's perfectly fine.
Yeah, they can see everything.
Perfect, okay. Good. So I'll continue. And I promise you guys, I finish on time. So at 6 o'clock, if you promise to go out to have a drink, you will go. Good. Perfect, thank you. So let's continue. So we discussed that in the ductility-based design, I have elastic response spectrum. I change it to inelastic response spectrum by dividing that to the reduction factor that is a function of ductility. This reduction factor is one, the simplest one for the very stiff structures, and it reaches to the ductility for them basically more flexible systems. And then that's easy. The pushover tells us the load displacement behavior. I can easily change this response here, basically the capacity to the load displacement or acceleration displacement behavior, and the intersection gives me the performance point. Bingo, it's easy. So basically, pushover is giving me the demand, how much basically the structure will be under pressure. And the red line, the inelastic spectrum, gives me the capacity. An intersection of demand and capacity is the performance point, is what will happen to the structure. And it's good because I can perform pushover analysis. I can push the structure to the performance point and exactly see what is happening at that point. So I use that concept, the ductility concept, to find the response parameter and also to find what is happening to the structure. From now on, hopefully the presentation would be nicer, okay? So less equations and fun. So let's look at the case. This is the basically the elastic response, and the red one is the inelastic. If it's elastic, we did this analysis. This is the green line, and the structure demand and capacity, they intersect here. So this displacement is if the structure was elastic. So can you tell me roughly what would be the maximum displacement of this structure, roof displacement, if it was if it was elastic? Can you tell me? It's between, is a meter, yes? It's between 20 to 30 centimeters. Shall we say 23? Agree? 23 centimeter? Yeah. If I draw a line from here, go down, is 23 centimeters. So if the structure was elastic, the displacement was 23 centimeters. Now, I chose that one on purpose. If the structure is inelastic, we have to look at the red curve and the black curve. And the performance point is here, yes? What is the displacement? It's between 10 and 20, yes? Shall we say 14? 14 centimeters. Think about that. Elastic was 24, for example. Inelastic, 14. It means that if the structure is nonlinear, the displacement of the system is less than the elastic. It's important. Remember, so if the structure is inelastic, don't think that always you have higher displacement. No, sometimes you may have lower displacement because the system can change its characteristics. Now, I skip this one, is the review I get here. The pushover analysis is good because it can tell me what is happening in the building. This is the pushover results. I pushed the structure and I looked at the base shear versus roof displacement. If it's linear, it means that the structure is elastic. Agree? If the structure is elastic, it means no damage. Yep, so no damage. Here is the beginning of the nonlinear curve. It means that the structure started damaging. So it's a light damage. Here, you have a lot of reduction in the stiffness and capacity. So the structure is moderately damaged. Agree? Here, it's just before collapse. The structure is extensively damaged. And here is end of the story. The structure is completely damaged. Agree? Now, I have two buildings, and they are put under two earthquakes. One earthquake is basically a strong earthquake, this top one, and one earthquake is moderate earthquake. And I have two buildings. Let's look at this, the first building here. And I want to know that what would be the expected level of the damage and the medium earthquake or low seismic demand and high seismic demand. Agree? Let's help me, even if you didn't get the previous slides, let's think together. I look at the first structure. The first structure Under low seismic is this point. Under high seismic is this point. Can you tell me at low seismic design, what is the damage? Look at this. Is it light, moderate, extensive? No. Can you tell me? You raise your hand. I see your hands. At this point, who thinks the damage in the building is no damage? No one. Who thinks the damage in the building is light? Raise your hand if you think. Here. Do you think that the damage here is light? No one. Who thinks it's moderate? Really? Be brave. Raise your hand. I can't do anything. I'm sitting in the UK. You're safe. Good. Perfect. Many of you think is moderate. And who thinks it's extensive? No. You are good. You are really good. I agree with you. Here is between 2 and 3. It's past 2, so it's after light. So it is moderate damage. Well done. I'm impressed. Well done. What about the stronger squeak? In the stronger squeak here, who thinks that it is moderate? Who thinks it is extensive damage? Perfect. Wow, you're much better than my PhD students. So you're right. Here, the structure is heavily damaged. So it is moderate damage in the lower squeaks and extensive, relatively extensive damage in the stronger squeak. Let's look at the second building. What is the damage here? I agree that it is extensive. Yes? Good. You're shaking your head. Good. I like it. What about the behavior of the second structure under a stronger squeak? They don't intersect. They don't reach. Yeah? You see, before it reaching this line, it goes down. What is happening? Can you tell me? Can you tell me what is happening for the building 2? Say in Spanish and someone can explain it to me if you don't comfortable to speak in English. Yes, can you say? What is happening for the second building? In my class, generally I have chocolate and I show them the chocolate. So give me the right answer, I give you chocolate. So I can show you chocolate here, but I can't give you the chocolate. So I answer yes.
Sir Iman, we have a question. What's the difference between the weak and strong? Like, what is it? Like one is brittle and the other one's not? Like what, or is it just the strength?
A very good question. The two buildings are, if you ask a building, it's true that the strong one has higher capacity and higher ductility. So both, it is a stronger and also more ductile. The weakest structure has less capacity and also it is brittle. The earthquakes are the two earthquakes that we do in the design codes. The low seismic one, I call it design-based earthquake, DBE, and the high one is the maximum credible earthquake, MCE. So generally, the normal buildings are the one on the top, okay? Good buildings. The bottom one is a bad building. In the low earthquake, it was heavily damaged, extensive, you told me. And in the strong earthquake, it did not intersect. It means that it collapsed. So the second building, basically it collapsed before reaching that point. It means that it is a bad design. So it is both capacity and ductility. Great. Now, give you an example. We use a SAP 2000 software. This is the building that we had, and basically a tall building. And we analyze it. These red ones are the basically demand, and this capacity, and this green line is the pushover analysis, that is demand, and intersection point gives us the performance point. So here I ask my students to do a project and they calculate this performance point. We can do it hand calculation or software. So what he did here is that we use the same building, two different types of concrete. One is a very bad concrete, 8 megapascal, and one it's a better concrete, 20. So with the 8 megapascal, you see that it was no performance point. It means that the building would collapse. With the same building, we just increase the capacity of the concrete and also the steel. And for the better material, now we have a performance point. So the structure survives. So even the same structure, if you use bad material, it fails. If you use better material, you can find out that what would happen to the building. So this method, ductility-based design, gives you tools to be able to control the response of the structure. You see here, by changing the parameter and the strength and of the concrete and steel is a reinforced concrete, I can find the response. Good. Now I go to the third part of my presentation, principles of performance-based design. We realize that in the normal design process, we try to control the damage. How? We assume the structure is elastic. We reduce the load by behavior factor, and we analyze the building. But we do not have any means. We do not have a way to control the damage. Performance-based design is a concept that can help us to control the damage at locations in a way that we like. I start with the design guidelines, a little bit about the performance levels and earthquake classifications and objectives, and then how we model it and how we can perform performance-based design in a practical application. And I'll show you a very simple example. So this is very easy. It gives you the principles. I chose a tower. It's a tower actually in Tehran and Iran. And I wanted to say that for normal buildings, you can do normal design process. But for special buildings, you really need to design it based on the actual response of the structure, and the performance-based design provides you with that opportunity. So performance design is helping us to control the damage both in the structural and non-structural elements. Helps us to control the damage to the level that we like. Helps us to design in a building that some part of the building is very strong and some part is not. I give you an example. You want to design a building, at one part your family is living, you want to design it in a way that those stories, they do not suffer any damage because your family is living there, yes? Another part, one of your friends that you had a fight with him is living, yes? And you want to design it in a way that during an earthquake, there is a big crack on his wall. So we can design it like this. The one that the part that your family is living is safe, the other part is not safe, yeah? So you have the power to control the damage. And also, based on the different types of structures, you can have different levels of the damage acceptable, and you design it exactly on the way that you like. But the problem is that you need more sophisticated methods to analyze the response of the building, but we just discussed, we can use pushover analysis or nonlinear dynamic analysis. The performance-based design started a long time ago, and when I started my PhD, and I don't tell you when because you realize how old I am. Actually, I can tell you. In 2000, the first version of the performance-based designs came, and my PhD was on performance-based design. And I remember people were telling me it's too fancy. No one is going to use performance-based design. I remember that I had this discussion in Sheffield with my colleagues. They're telling me you are wasting your time. And they were right. I was absolutely right. Performance-based design is the future of seismic design. And all the design guidelines are moving towards performance. Now we have new generation of seismic design, performance-based design methods, IABSE codes, and different countries, they adopt different versions and different forms of that. So this is the future of earthquake engineering and is very well established after 20-something years that I started my PhD. Now, let's discuss. This is basically a picture from a recent earthquake at the border between Iraq and Iran. I took the picture on purpose. Do you think there's an acceptable design? Do you think it's a good design? No. No. So the principles of seismic design may not be, at least could not protect this building. Look at this. The other buildings in the behind are okay. This building completely collapsed. So we start thinking that how we can define acceptable design, and then how we can ensure that we will reach the acceptable design. Agree? Now, We define different performance levels for the buildings based on the level of the damage that we observe in the building to the structural elements and non-structural elements. The first response, so the first basically performance level, it's called operational. It means that we have negligible damage, very little damage. It means that if it's a hospital after an earthquake, the hospital can accept patients. It can work with no problem. The second one is immediate occupancy. They call it IO. It means that the structure is lightly damaged. If you're in your building, an earthquake happened, it means that you can repair your building quickly. And I'll always give this as an example. If it's in my building, an earthquake happens, if it's immediate occupancy, it means that I can sleep at my bed tonight. You know, I should have my own pillow. If I change my bed, I cannot sleep. So if an earthquake happens and is immediate occupancy, it's good because I can use my own bed and I'm happy with that. Yeah. Life safety is a moderate damage. It means that the building tries, it is damaged structurally and non-structural elements, but it tries, not in short, it tries to control people's life as much as possible, the injuries, the mortality. So it is the design that we generally target for normal buildings when we design it for them, basically earthquakes. Collapse prevention, it means that the structure is heavily damaged, but it's not collapsed. So generally, at the life safety, the building is repairable, but at the collapse prevention, no. But many people, they unfortunately die, but at least the building does not collapse. And the collapse is bad, is red. It's sorry, I put it in black. It's bad. So it means that end of the story, and we don't accept it. We can't accept the collapse. Agree? So this is the definition. Now, like, look at it a little bit more. You know, you don't have Costa coffee. Yes, most probably you have a Starbucks. Do you have a Starbucks there? Do you have for coffee? Yeah. Yes. Imagine that a Costa. Oh, okay. Costa is the UK's Starbucks. Okay, it's everywhere, and I love coffee. I drink coffee like crazy. So this is a Costa tea. So basically, when the structure is fully operational, it means that after an earthquake, you can say that, okay, we had an earthquake, let's go and have a cup of coffee. Fully operational. You go and you will have your coffee. Immediate occupancy, it means that after the earthquake, your favorite coffee shop is damaged, but it can be repaired. You don't see any serious damage. Yeah, we can say that it's closed today, but next week I will have a cup of coffee. But for collapse prevention is extensively damaged, and you have to find another coffee shop. Your coffee shop is gone, unfortunately, and it's not repairable. So let's provide more detailed information. We are engineers, so let's discuss. It is operational. No permanent relief should be observed. The structural components should keep their strength and stiffness. Yeah. So no extensive damage. Facades may have minor cracking, partitions, but not the structural elements. And all the important systems should be operational. You should have light. I told you it's an hospital. So basically, after the earthquake, they may accept patients. They may do surgery. So all the necessary parts should be working. Remember, I will ask you questions. Okay? Listen to me. I will ask questions soon. Immediate occupancy, it means that some damage, but not extensive damage, some minor cracking. Elevators should be working most probably, but the fire protection system should be operable. But a structure keeps most of the keeps most of the strength and stiffness. Some level of damage is acceptable. Life safety, the structure strength and stiffness is reduced, but you have just some residual stresses not to fail. The load bearing capacity, the gravity load should be intact. Those elements should be good. So the gravity load bearing elements should be functional. Out of play failure of the walls should be prevented, because out of play failure will kill people, will injure people. because it falls over people. So for life safety, we want to minimize out of plane failure of the walls is important. Some permanent drifts, it means nonlinear deformation exists, partitions damaged, and the building may be beyond economic repair. It means that we may not be able to repair the building. It will be too costly to do that. And collapse prevention, a lot of damage, just a little bit of a stiffness and strain remains. We have large permanent drifts. Even some of the exits are blocked, and the walls are fell over, and the building is close to collapse, but is not collapse. And almost always it is beyond economic repair. It's too late. You can't really repair it. You have to demolish the building and make a new one. Now, let's see these pictures one by one. So I repeat the levels. It is operational, agree? Immediate occupancy, life safety, collapse prevention, agree? What is this one to you? Who thinks that this is operational? Raise your hand if you think it's operational. Operational, I repeat again. Operational, immediate occupancy, life safety, collapse prevention. Who thinks it's operational? Who thinks it's, none of you, no? Who thinks it's immediate occupancy? Really?
No.
No. Who thinks it's life safety? No, you're absolutely wrong. This is very little damage to me. I like this conversation, okay? So, and I can't prove. My idea is that this is operational. Why? You see these cracks here? Yeah, I think you're afraid of these cracks. To me, they are in the on the walls. They are not structural. You see, even the windows are not broken. Yeah, the doors are not broken. So to me, these are not really as heavy structural damage. So the building is, to me, is operational or immediate occupancy. Okay, immediate occupancy. It means that you can quickly repair it. Maybe I change it to immediate occupancy, but this is not really damaged. As I said, even the windows are not broken, but it's good because we have some disagreement. I like the disagreement. I have a point. This one. Who thinks immediate occupancy? No. Who thinks life safety? Some of you. Who thinks collapse prevention? Some of you. Who thinks collapse? Of course, it's not collapse. Yeah, I like it. I think you are a little bit more careful than me. I accept more damage. You don't accept. To me, is life safety. Okay, is life safety. Is some damages here and the buildings. Yes, and agree. To me, is life safety. What about this one? Who thinks is life safety? Who thinks is collapse prevention? Really? To me, still is life safety, guys. I like it. So to me, it's not close to collapse because you see the columns are intact, the connections are okay. So the connections are okay. The failure was mainly due to the walls. So it is, to me, is maybe life safety, not too much towards the collapse, but it can be collapse prevention as well. Okay, I agree. What about this one?
Let me tell them something real quick. Esto es algo bastante subjetivo porque no nos está dando como unos criterios numéricos para definir, ¿cierto? Entonces está bien si no, pero la principal diferencia entre life safety y collapse prevention, en collapse prevention está a punto de caerse, ¿cierto? Ese edificio está a punto de caerse, no tiene pinta de a punto de caerse, ¿cierto? Entonces, ahí más o menos como lo podrían discernir en ese sentido, pero estoy de acuerdo que es bastante subjetivo. Hay maneras de hacer esto objetivamente, o sea, con números, ¿cierto? Pero ahora mismo es un ejercicio académico. Okay. I was just trying to explain a bit of the difference between the two and all of that.
Perfect, perfect. And please feel free to jump in and help. Thank you. That's great. So this one, who thinks is life safety? Who thinks it's collapse prevention? Who thinks it's okay? Some of you. Who thinks it's collapse? So again, to me, it is between life safety and collapse prevention. I would say life safety, to be honest, but some of my colleagues, they think is more than life safety. Again, look at that. Some of the walls are fell over, but the exits are open. Yes, the column beams are intact, they're there, and the building is not close to collapse to me. So it is excessively damaged. So most probably is at the end of the life safety region. Okay, but maybe it goes to the collapse prevention, but mainly life safety. So I'm choosing this one by one. You know, every time is a little bit more damage. What about this one? Who thinks it's life safety? Who thinks it's collapse prevention? Okay, good. I agree with you. I think this is more towards collapse prevention. Is more than, yeah, because it is heavily damaged and a lot of basically walls are fell over. So for this one, to me, is collapse prevention. This one may be in between. What about this one? Who thinks is life safety? Collapse prevention? Perfect. Perfect. Collapse prevention. Well done. Well done. What about this one? Who thinks it's collapse prevention?
Professor, in the previous photo, didn't it collapse already? Isn't there like a sub-story?
A very good one. I don't think so, because to me, you see, is still, you know, the story remains the story. Is a little bit deformed, but it has not disappeared. Okay? Unless you say here something you think, yes?
Yeah, that looks like a whole floor collapse.
If something is like this, I agree, yes, but the picture is not very clear. If one story is collapse, totally agree. Is a collapse, I agree. But if I ignore that part, is that clear from this picture? I thought that is a little bit of the damage. If it's like that, yes, it goes to the collapse prevention. Very good point. What about this one? Who thinks it's collapse prevention? Who thinks it's collapse? Yes, it's collapse because this part of the structure is fell over. So it's already collapsed. Agree? What about this one? This building. I think it's easy. Yes, it's collapse. Agree? And the most difficult one is this one. What do you think? Obviously collapse. Yeah. So you notice that for some of them we agreed. For some of them, no. Because we talked about the behavior in a general way. Now, the performance-based design methods provide us with more detailed methodology, something that we engineers we can use. For example, the code is from FEMA, this one. FEMA is, you have a free access to FEMA code, and is the base for many of the other performance-based design guidelines. This is the damage control for concrete frames. It says that, for example, for immediate occupancy, you accept this level of the cracking. The width of the crack should be like this. And for life safety is this one. For collapse prevention, this one. So it starts looking at the response of the elements, cracking, and the capacity, and explain you what would be acceptable or not. They have the same tables for example, here for steel moment frames. It talks about the local yielding, local buckling, connections. I don't have time to read on that. You will have the copy of my presentation if you like. And based on the behavior of the hinges and connections for the moment resisting frames, the steel, you can categorize them in different groups. And also for brace frames, is based on the yielding or buckling of the braces and the connections. You can understand this immediate occupancy, life safety, or collapse. So these ones, when you go to the site, you look at these things, you can understand. But there are better ways as well if you use especially analytical models. There are two parameters that are generally controlled in performance-based design guidelines. One of them is the maximum interstory drift, lateral displacement of the system. It says that, for example, for the concrete frame, if the lateral displacement is 1% of the height, is immediate occupancy. It reaches 2% is life safety, and if reaches 4% is collapse prevention, and beyond 4 is damaged completely. And this column here shows the permanent drift. So basically, by looking at the you analyze the building using pushover analysis or nonlinear dynamic analysis. You calculate the drift, and then you can use these tables and easily say that what is the level of the performance. This table is for concrete frames. This table is for steel moment frames. So these are different numbers because of the way that these structures they experience damage. And this is the one for steel brace frames. So for each type of a structural systems, they have that the acceptable ranges like this. Good. So we could look at the pictures and, like what I did, argue about the performance. We can run the models or measure the displacements, and based on that, decide about the overall performance. But there is another way as well. We discuss it in a few minutes, that even they provide us more detailed information at the elements level. Now, we discussed about the damage and elements, but at the same time, we have earthquakes, and we have different levels of earthquakes. We have earthquakes that they happen frequently. The written period, I said 43 years. It means that if the effective life of the building is, for example, 30 years, 50% chance that they happen during the effective life. We have occasional earthquakes. Their definitions are different in different codes. Rare earthquakes, this is the one that we generally use for design. So written period 475, if the effective life of the building is 50 years, 10% chance that we have earthquakes stronger than this. It means that if you design your structure based on this, 90% you are safe. Very rare, and MC, again, codes generally, they control these two. They design based on the 475, and they check for the 2475. This is the earthquake that just there is 2% chance that something stronger than this happens during the effective lifespan of 50 years in the building. So these are the two. So now in performance-based design, this is taken from FEMA. You are dealing with two basic different parameters. One is the earthquake, this side. It shows that this is basically, I'll tell you, this side is the earthquake. This side is the performance of the building. And this vertical line shows how much material I need or how much money I have to pay. So generally, the code, they go for these two. It means that they say that we want to control collapse for the very strong earthquake. So the intersection is P. And they control the life safety for the 10% chance, or here I told you here, rare earthquake. So this K. So the codes generally for the normal buildings, normal codes, they satisfy P and K. If you look at this nice sphere, you realize that if you satisfy P, you automatically satisfy I, H, and D. Because if the building has not collapsed under very strong earthquake, it will not be collapsed under weaker earthquakes as well. You satisfy K, you automatically satisfy G and C for the same reason. But the others, you don't know. Others, you don't know. Are you going to satisfy J? Are you satisfy E? No. In performance-based design, the good thing is that the normal design looks at these two, and automatically these will be satisfied. But in performance-based design, you have the option to do whatever you like, design based on what you like. Code helps you. First of all, the code categorizes the buildings into different groups. Safety critical facilities are those that are really dangerous. If something happens, like a nuclear power plant, something happens, they kill hundreds of thousands of people. Yeah, so they are safety critical facilities. Then we have essential or hazardous facilities. Essential facilities are the facilities that we need them after an earthquake, like hospitals, communication centers, police, fire stations. Or hazardous facilities like the refineries or oil reservoirs, something that if earthquake happens, for example, explodes. The difference between hazardous and this is that for the hazardous, for example, if something happens, it kills 200 people, and in this case, it kills 200,000 people. So there are different levels of danger. And normal buildings like our building, the buildings that is my house now and your university, they are categorized as basic facilities. Okay. Now the code, the performance-based design codes, they tell you how you need to do design. It says that for the basically ordinary buildings like your university, it says if a weak earthquake happens, it should be in operational level. If the design-based earthquake, this one with the 475 years written period happens, it should be life safety. If the strongest earthquake ever happens, it should be collapse prevention. So we don't let the structure collapse, because if the structure collapses, no one would expect to leave the building alive. For buildings like essential buildings, hospital, it says that if a weak earthquake happens, fully operational, it should accept patient immediately. For the design earthquake, operational, it means that you should be able to repair your hospital in 1 or 2 days. And if the very, very strong earthquake happens, still it should be life safety. It shall not kill the people, poor people that are already in the hospital. Yeah. And for the very essential buildings, like the one that, for example, we had in Japan, if the the design earthquake happens, it should be fully operational. Nothing happens to the building. And if the strongest earthquake happens, in that case, it should be operational. And you remember, in the last earthquake in Japan, it didn't happen. Why? Because tsunami actually damaged the building, the nuclear power plant, and it moved toward life safety and even collapse. Yes? So it's very dangerous. And it was because of the secondary hazards. It's not in the scope of my talk, but these are things that should be considered. So this is the target. Now, I provide you more information. How we can do that? We have the pushover analysis. Based on the pushover analysis, the same coffee shop that I had. Now you can say that at each stage, what level of damage you have. We already talked about that when it's almost elastic is immediate occupancy, when it's heavily damaged is life safety, when it's before collapse is collapse prevention, and here is collapse. So based on the behavior of the pushover and the maximum displacement that the system experiences, we can understand what is happening in the building. Now, because they have methods how to calculate this maximum displacement. I told you just now, ductility-based design can tell you what is the displacement, target displacement, but there are other methods. I don't teach them now, but there are methods that you calculate a few coefficients, and based on the period of the building and coefficients that they relate on the behavior of the elastic inelastic system and the multi-degree of freedom and even a strengthening hardening ones, you just simply multiply a few numbers and you have the maximum displacement of the system. You can use the FEMA method. There are 3 coefficients, and you can use ASCE 41. There's a new generation, and there are 2 coefficients. And it's very easy if you like. This is an equivalent of the ductility-based design method, easier to do. So you calculate the displacement by using these equations, and then you have pushover. We find the displacement. Now, in this response, it is beyond immediate occupancy, because immediate occupancy was here, collapse prevention was here, life safety here. Yes, I written here, life safety. So what is the performance of this point? Can you tell me in this structure? Who thinks is immediate occupancy? Raise your hand. Who thinks is life safety? Raise your hand. I think I confused you. So this is the pushover of the building. This is the displacement of the building. It is beyond the immediate occupancy. So the damage is more than immediate occupancy. So it means that the damage in this building is life safety. Agree? It's between these two. It's beyond this. It's after this. Is after immediate occupancy. So the building in that case is life safety. So what we did is that we calculate this displacement by either this method or ductility-based method. I perform pushover analysis and I check this displacement and say, oh, this building is in this life safety performance. And now, basically, to analyze the buildings, we discussed that we use inelastic response, the backbone curve. We discussed about that. And the code helps us to do this. So what it does is that the code says that let's help you. This is the backbone response that you want to use for modeling. Agree? So the code makes it easy for us and says that in your model, basically, this is the response of your element, beam, column, brace elements. This is the force, normalized force, and this is the displacement. And it has two levels. P means that primary members. S means that the secondary members. For us, we look at the primary members, okay? P means primary members. It says that if you have this response for the elements, if that element, that beam or column, the pressure is here, or sorry, before here is IO response. If it's between here to here, sorry, between here to here would be life safety. Is between here to here would be collapse prevention, and after that is collapse. So basically, exactly based on the concept that I have here, for each element, I can basically tell you what is the performance of that specific element. This beam is life safety. That beam is collapse prevention. That column is immediate occupancy. So you can control all the elements exactly at the level that you like. So this is the whole idea of that. And then they make it dimensionless. So they divide the force by the yield, divide the displacement or rotation, depending on the type of failure. If it's a plastic hinge is rotation. If it's elements, for example, brace elements is delta. And what is interesting is that if I look at the load divided by yield, the first point is always 1. Yeah, because this is a yield point. Yield divided by yield is 1. So practically, if you have these parameters A, B, and C, you can have the overall response of the elements. That one curve. If you have the numbers for IO, LS, and CP, you can understand that what is the performance of that element. How can we find these numbers, these 3 numbers for the modeling and these 3 numbers for the assessment? We have it in the seismic performance codes. They are already provided. This table is from FEMA.
Professor
Yes.
Iman,
Yes.
Sorry for interrupting
Sure.
you. We have 10 minutes left.
Sure. I try to go faster. So,
yeah. Thank you very much.
They're almost okay. So what we do is that we have these numbers, we model our structure based on these numbers are already provided. And then I give you an example. This is the building. I use SAP 2000. Those numbers are already included. And you see that after an analysis based on the rotation of the elements, now it says that this hinge and hinge are in the immediate occupancy and this hinge and hinge in the life safety. So it's very easy to do, to find the response. Yep. And the good softwares like SAP, they have it already. The last part of my presentation that I go briefly is performance optimization, performance-based optimization. Now we learned how to design for performance-based. Let's see that how we can optimize the design. This is a challenging area. Why? Because the system is inelastic. Generally, if we have the structure under the load, is what we design. We design the building under lateral load. We apply the actual earthquake. We look at the response of the building. This is the damage ductility. We realize that the building is not damaged proportionally. It's the blue one. Some parts of the building is heavily damaged, some parts no. So the performance-based optimization means that the material that you didn't use, move it to the parts that you use, and eventually you can find a state of uniform damage. It means that here, if you can find the optimum answer, everywhere will be damaged the same performance. It means that you use the full capacity of the building. It means that instead of using this load, you have used a different load pattern. I have like 10, 12 publications on this area, and I realized that this optimum load pattern that will distribute the damage uniformly and use the capacity of the building everywhere is different. It depends on the period and ductility of the building. You know the definition of ductility. So the codes generally, they don't consider ductility, just look at the period, but I suggested a formula, a few papers on that you can see. And if you use this formula, it can give you a load, you design it, and you have much better performance because you distribute it uniformly based on the performance. Apply this method for shear buildings, truss-like structures, steel frames, reinforced concrete, FRP strengthening. My next presentation, 2 weeks time, would be on passive control systems on this and solid structure interaction. I give you an idea. That's very interesting. I optimize this truss-like structure for different ductility levels. And you realize that the optimum answer depends on the level of the ductility. So optimization methods that people they use based on the elastic response is not accurate for seismic. For seismic, we have to accept damage. We have to have nonlinear performance. So remember, 90% of the optimization methods, they go to the garbage now. One of the few methods that can be applied is this optimum performance-based design method that we developed for years now. And I realized that by using this, I can reduce the weight of the structure by 40%. So I give you a structure that is 40% lighter. I applied this method for more efficient design of steel structures. You see it here for the bracing system. These are the equations that I use. This system can optimize the response very, very quickly. I showed here after a few analyses, like 6-7 analyses, this is the damage interstory, basically drift. You see that from the structure that was heavily damaged on the top, I changed it to a structure that is almost uniformly distributed. How many steps? 9 steps. If you want to use other methods like GA, you need most probably 900 steps instead of 9. So it is at least 100 times faster than the other methods. And here I checked at the damage. You see a step by step. This is the code design. It's the design that you do it now if you use your code. And it's a design that after my proposed optimization, performance-based optimization, you will see that you reduce the damage after 4 iterations significantly from 40 to less than 15%. Yes, amazing. We apply that for the other type of structural systems. Here is the way that we apply for reinforced concrete frames. And you see the response. This is the original design based on IBC. And after a few steps, this is the one that we optimize it. You see here, damage is uniformly distributed, and the overall damage is much, much less than what the code says. We move the material from parts that we didn't use to the materials to the part that we really need. Original structure was 30% damage. We reduced the damage to 20%. So basically, considerably reduction if you look at the ratio. This is the optimization step, and I want to show that this parameter is very important. I spent a lot of time on this parameter, and I have methods to find this parameter accurately. And you realize that our method, less than 10 steps, reaches the answer. I told you for normal, I have methods that compare, papers that compare with GA or particle zone optimization. You can even do it by Excel, but normal circumstances, you need close to 1,000 number of analysis. So something that we optimized with GA and the computer was running for 6 or 3 months, with my method, we can have the answer in 1 hour instead of 3 months. Perfect. I finished my presentation here, as I promised you, on time, with a nice picture from our department. This is the Department of Civil and Structural Engineering at University of Sheffield. And I repeat, if especially our postgraduate students, they want to visit us, more than happy to host them. And Sheffield is a beautiful place. We have nice places around the city. I'm sure you will enjoy your time. Thank you very much again for your invitation, and it was really my pleasure to give this presentation.
Thank you so much for your lecture.
Thank you. Most probably we don't have time for the questions and answers because I already used all my time. But if you have questions, it's very easy to find me. Send me an email, and I will send a copy of my presentation if you like as well. I'm happy to share it with you. And finding me is very easy. Search it, search guys, Iman Sheffield. I think that I'm the only Iman at the University of Sheffield. So Iman Sheffield, you will see my webpage and my email address. Thank you.
Professor Iman, thank you very much for your time on behalf of the IABSE National Group, Colombian National Group, and the Universidad del Norte. Thank you. We appreciate your time.
Thank you.
And I appreciate your sharing your knowledge with the students at the university. And thank you very much, students. I don't know, Jorge, if we have time for questions. Otherwise, we can end this event today.
We have the room until 6, so I think it's better if we just like finish now, and then we still have another space with Professor Iman in 2 weeks, so we can have any questions then.
Exactly. Actually, the other presentation would be extension of the optimization. So if you listen to me today, you will understand what I will explain in a much better way in 2 weeks' time. Yeah. Thank you again for your invitation, and we'll keep in touch.
Thank you very much, Professor. Hasta luego a todos, que estén muy bien. Muchas gracias a todos en la universidad, a Melissa, Carlos, Jorge y a todos los estudiantes. Espero que haya sido una muy buena experiencia para ustedes.
Hasta luego, chao, Juan. Muchas gracias por todo. Hasta luego.
Hasta luego, que estén bien. Bye, bye, profesor. Keep in touch.